reflections in horizontal line, followed by reflection in line 45 degrees, which we called R. So remember, we have H, R, V, and L. And then we have, if we multiply that by sigma on the left, sigma rho, then we will have it equal to rho cube sigma, believe it or not. You will have to, after I write all possible rows here, rho squared and rho cubed, to check everything that I write here, but most important part would be checking the last column. So rho squared, of course it's a rotation by 180, so this can be written as sigma h, sigma v, and rho cube by 270, so this can be written as sigma h, sigma l. And if we multiply on the left sigma rho squared, this is the same as rho squared sigma, and here if we multiply on the left, this is the same as rho times sigma. So at this point you should stop and really check everything that I've written, calculate. I will show you how to calculate, let's say, this one, y. So we'll start with sigma rho on the left. That is the same as, remember, sigma is just sigma h, and rho is sigma r, sigma h. So sigma r and sigma h. So this can be rewritten as rho to the fourth, because that's identity on the left, or rho cubed times rho. That's the identity. So we can always add it on the left. And after that we have sigma h, sigma r, sigma h. And the last row, rho cube I would like to leave as it is, and this row I would like to write again as sigma r, sigma h. Times sigma h, sigma r, sigma h. So we have cancellation here, then after that this and this will cancel, and we'll be left with sigma on the right multiplied by rho cube, just as we should have. So this is checked. Go ahead and check everything else. Okay. So with all those equations in place, it's really easy to fill out the Cayley table for the group. So which shows us all possible products. So what is the Cayley table? So we have dihedral group of regular square. So polygon, regular polygon with 4 vertices, D4. So we said that there are 8 possible elements in this group, starting with identity, followed by rho, rho squared, rho cubed, rho to the fourth is identity again, and then we will multiply, let's say on the right, everything by sigma. So then we have sigma, rho sigma, rho squared sigma, and rho cubed sigma. And here we have the same elements, identity, rho squared, rho cubed, sigma, rho squared, sigma, rho cubed, sigma. So it's trivial to fill out the first line, it would be just, the first row would be just repetition of the top row there, then multiply by row, everything will be clear, row squared and row cube, so you just write it, for instance, row cube row would be row cube, row to the fourth is identity, row to the fifth is row to the sixth is row squared, row cube sigma, row fourth is identity times sigma, row to the fifth times sigma is just the same as row sigma, and finally row to the third times another row to the third, that's row to the squared sigma. As long as they are in the same form, rows on the left, sigma on the right, then we have what we want. We represent these products as one of the known elements of the group. But what do we do here? This is the most difficult element, most difficult row to write, because we have to multiply by sigma on the left. So we get some combinations which are not looking like elements that we represented originally, rows on the left, sigmas on the right. Here we will have some sigmas on the left. So then we have to use those identities. And we should be able to commute or to change places sigma and various rows. So how do they change places? Of course they do not commute. So if we have sigma times some row to some power, what can we say about this transformation? This is an isometry, obviously. It's several rotations followed by reflection. What can you say about this? Several rotations composed to a rotation. And this would be rotation around the origin, while sigma is a reflection along the horizontal line, which also passes through the origin. So a rotation times a reflection through the same line. If you write the rotation as a product of two reflections through the same point, all of the lines will be passing through the origin. Then you know that this product must be a reflection. Even transformation times a reflection will give you, well, in this case it will be just a reflection through the origin. So then it means that this, since it's a reflection, it must be an involution. So this is reflection, hence involution. In other words, the inverse is the same as the original. So if we invert sigma rho k, we should get the same exact isometry. Well, but if we do, then we have to write rho to the negative k in the first place and sigma inverse, which is sigma again, on the second place. And rho to the negative k is the same as rho to the n, well, rho to the 4 minus k times sigma. And that's why all of those laws, all of those identities hold from these considerations. Of course you can find them directly, hopefully you have done it, but you can also see that just from the fact that it's an isometry, that it's a reflection in the line around the origin, then we have to have this general identity. Okay, so finally we have, please fill out the Cayley table, finish, and we know how to compute multiplication of any two elements in this group. So we have the complete description of the group of isometries of perfect square. So let's now figure out in similar detail the group of isometries of a perfect